Hey Trigoners, welcome to our probability unit. This unit actually doesn't start with probability, but rather starts with an idea called counting. A little more than just basic counting. So I want you to just take a look at simple enumeration. So if I asked you how many squares are on the checkerboard, most of you probably would not count out 1, 2, 3, 4, and so on. You'd more likely do 8 times 8 to get 64. It gets extremely tedious to count 1, 2, 3, and so on. So today what we're going to institute is the multiplication principle, which is also sometimes called the fundamental counting principle. Basically, it allows us to count faster. So consider the following scenario. We flip a coin and throw a single die. What are all the possible outcomes? As in, I could flip ahead, then a 1, flip ahead, then a 2, flip ahead, then roll a 3, and so on. Now the total sample space, or total number of outcomes, isn't that great on this problem, so we actually could count them. Often we use something that we call a tree. So here in this tree, you can see the organization. If I were to flip ahead, roll a 1, I'd get the outcome of a heads, tails. If I flip ahead, then a 2, my outcome is heads. Sorry, I said heads and tails. I meant heads and a 1, then a heads and a 2, and so on. If you counted up all of our possible outcomes, you'd see that we have 12 outcomes in our sample space. However, if we're going to use the fundamental counting principle or the multiplication principle, what we can say here is that we have 2 possible outcomes here, 6 possible outcomes here, so combined the total number of outcomes would be 2 times 6, or 12 possible outcomes. In this case, I'd say it's pretty easy to count these up just using a tree or kind of counting on your fingers. Now, consider the next scenario. You're at a math party and you'd like to take a bunch of trig selfies to post on Facebook, obviously. How many selfies will you need to take if you wish to have a selfie that includes you, and one of each of the following? So 4 friends you have to choose from, 3 backgrounds you have to choose from, and 6 math books. So basically, here's you. You can choose 4 friends. So let's say you choose friend A, background A, and math book A. You could also choose friend A, background B, and math book A. Friend A, background C, and math book A. Do you get the idea? Now, basically, we'd have to go through and find all these possibilities. And if you're thinking ahead with me, that's a lot. So instead, what we're going to institute is the fundamental principle of counting, all right, also called the multiplication principle. Instead of doing all this, what I can say is that I have 4 friends to choose from in my picture, 3 backgrounds to include, and 6 math books to choose from. When I do that, I find that there's 72 possible ways to organize my selfie. All right, what this is called, again, I've been saying it over and over, but is the multiplication principle of counting. If a task consists of a sequence of choices in which there are P selections, just like we had 4 friends for the first choice, Q selections for the second choice. In our last example, we had some different backgrounds, and then R selections for the third choice. Then the total number of selections is just determined by their product, P times Q times R. So let's go ahead, let's up it a little bit. So consider license plates. So there's a lot of different combinations here of license plates. So think about this. From the 26 letters in the alphabet, how many ways can 4 letters appear in a row if no letter is repeated? So we know there's 26 letters in the alphabet. So basically what we're saying is we have 26 choices for my first letter. The second slot, I also have 26 choices, because letters are allowed to be repeated. Again, 26 choices, and finally here, 26 choices. If you go ahead and you multiply these together, or you just say 26 to the 4th, you'll find that there's 456,976 possible ways to arrange these letters. Now, let's make it just a touch harder. Not much, though. If I say from the 26 letters in the alphabet, how many ways can 4 letters appear in a row on a license plate if no letter is repeated? That means once I've chosen from the 26 possible for the first, whether I choose S or A or whatever letter, I now only have 25 options for my next. Then I have 24, and finally 23. Now again, we're talking obviously about the English alphabet, A through Z. This would differ if we were in a different language. All right, when you go ahead and multiply these, we should have less ways than the previous example. When you multiply these, you get 358,800 ways. You certainly would not want to make a tree diagram to figure out how to count those ways, obviously. So what I want you to do is go ahead, pause the computer, read through these two examples. These are actually how non-personalized license plates are determined in Illinois. Non-personalized meaning it doesn't say Griffin Math on my license plate. Take a look at your parents' license plate. See if they match this pattern at all. So go ahead, try these, pause, and then I'll have the answer ready for you when you come back. All right, in this case, on the first one, you had a 1 through 9 to choose from. If you do that, you have 9 digits there. The middle 5 numbers, you can choose from anything 0 to 9. There's 10 possible digits there, so those 5. You have 10 options. And then finally, the last digit, we're back to just 1 through 9. When I multiplied these out, I found that I had 8,100,000 ways to arrange those. In the second example, you don't get to choose any letter from the alphabet. You can only choose from those 18. So 18 for the first. And then the rest, you're able to choose any of the 10 digits. All right, if you think about it, I looked this up. There's right now about 12.88 million people living in Illinois. When I multiplied this one out, I got 18 million, just so you know. 18 million ways. This would cover... Just these two arrangements would cover all the people just in Illinois. And that doesn't even count the personalized license plates. So I'm going to just talk through one more idea. You've probably already realized, but what I've just talked about is an independent event and a dependent event. So an independent event means that the first event, it does not affect the outcome of the next event. For example, if I choose those 4 letters from the alphabet and then the next I'm allowed to choose, again, any letter without them being repeated, those would be independent events. So here, in this case, Mary has 5 concert t-shirts and 6 pairs of pants to wear for a party. How many ways can she make an outfit from these clothes? So when I look at the possible t-shirts, I say that there's 5 t-shirts. And then I get to pick a pair of pants. The number of pants is not affected by the t-shirt that I pick originally. So 5 times 6, which is 30 different combinations of outfits. So I'm going to say 30 ways I can pick outfits. And then in a dependent event, we'd say that the first event actually does affect the outcome of the next event, and the next event needs to be adjusted to reflect that first event. So in this case, each player Monopoly uses 1 of 6 pieces. How many ways can 4 people choose a board game piece? Well, the first guy that picks, he can choose from all 6. All right, then the next person can choose from 5, and the next person can choose from 4, and finally 3. When you multiply those together, the answer to that question, I got 360 here just so you know, 360 ways, each subsequent outcome is affected by the original picker, the person that came before them. So these are really just the basics, you guys, of counting, and we'll pick up from there. It'll get a little bit harder on Monday, but if we start with a really strong foundation of the basics, hopefully we'll have a really strong chapter. See you guys on Monday. Bye.